Okay, so now we're on to section 3.7, which is about applications. Now we have been talking about some applications. We've been talking about velocity, acceleration, and also tangent lines, but really calculus and in particular derivatives appear everywhere all the time in natural and social sciences. They really appear in arise because we are often trying to find the relationships between two variables. Um, Sometimes we will have sort of laws, laws of nature, Newton's laws, whatever, that give us equations, and then those sorts of equations we can then apply calculus and derivatives to. Or sometimes we might use statistics or some sort of way of fitting a curve to some data we have, and then that curve is a function, and to that function we can then apply calculus. So that happens a lot in social sciences. So let's see some examples of applications. So the first example we're going to look at is something called linear density. Now you've probably heard of density before. Density is mass divided by volume. What is linear density? Well, that's when we're looking at something like a cable, a rope, a piece of wire or line, or a rod, or some sort of object which comes, some sort of material which comes in sort of basically a linear dimension. So the linear density of something which has constant density is going to be mass divided by length. Instead of mass over volume, it's mass over length. So how much mass is there per unit of this thing? Now, you might have some sort of wire, cable, or whatever, where the density actually is not constant throughout the whole thing. Sort of suggested by this picture here, where the lines are supposed to represent, thicker line or more densely packed lines are supposed to suggest a denser material, less densely packed lines, less dense material. So what we can do is we can measure how much this material weighs between one end and x units of this material. So then then we get a function, the mass up to x, how much x meters or whatever of this material weighs. The linear density then is going to be the limit as delta x goes to 0 of the change in mass over the change in x. We can take an average density of a piece and then let the length go to 0, and that will give us the linear density, which is a derivative. It is m prime. So for example, the mass of the first x meters of a length of cable is given by m of x is equal to the square root of x, which is x to the 1/2 kilograms. The linear density is then m prime of x, which is 1/2 x to the minus 1/2. And it's important for us to get the units in there, so let me write that in. This will be kilograms per meter, because m of x is in kilograms and x is in meters. Another example is current. So when we have electricity flowing through a wire, that's really electrons moving along through the wire, and we're probably interested in how fast this charge is moving through the wire. So the way we describe this is we take a red surface, sort of a slice of the wire, described by this red surface here, and we see how fast these blue particles, which are represented by, or supposed to represent electrons, are flowing through this surface. So let's let Q be the amount of charge that has passed through the red surface up to a particular time t. So we know how much charge has moved through the wire with respect to time. And let's let t be time. Then the rate of change of charge is dq dt, which is the current. Now Q is measured in coulombs, the basic unit of electrical charge. Time will generally do seconds. Current is going to be coulombs per second, which is amperes or amps. So for example, let's suppose that the charge that has flowed through this red surface up to time t is given by 1 minus e to the minus 2t coulombs. So it's probably worth your while to graph out this function, see what it looks like, and t is in seconds. Then the current is going to be the derivative of charge. So I take the derivative. The derivative of 1 is 0. The derivative of e to the minus 2t is, by the chain rule, I bring down the minus 2 in front, and e to the minus 2t, the derivative of e to the whatever is e to the whatever. So I get negative 2 times e to the minus 2t, but there's a minus there, so I get 2 times e to the minus 2t coulombs per second, which is amps. Okay, so we've looked at a couple of physics examples. Let's look at a biology example. A very common place for us to look at derivatives in the context of biology is in terms of population growth. So we can represent the size of the population of bacteria, animals, plants, whatever, people, by some function p of t. That's going to be our population at time t. Then we're often interested in how fast is this population growing, or is it shrinking, things like that. So that is represented by p prime of t. That gives us the absolute growth rate. That means for each unit time t, how much is the population growing or decreasing in absolute terms, in the number of organisms. We're also often interested in p prime of t over p of t, which gives us the percent growth rate. And we'll talk about that in the context of section 3.8. So let's look at some examples here. Okay, for example, let's take a culture of bacteria that starts with a population of 300 cells at time t equal to 0. Let's assume the population doubles every hour. So first, let's model the population p of t in the number of cells after t hours. So at time 0, we have 300 cells. At time 1, we have 300 times 2 cells, which is 600 cells. After 2 hours, the population is doubled again. We have 300 times 2 times another 2. That's 300 times 2 squared. So each hour, we're just multiplying the population by 2. After t hours, then my population is 300 times 2t. Now let's find p prime of t and p prime of t over p of t, which is the absolute growth rate and the percentage growth rate. So when we find p prime of t, we take the derivative of 300 times 2t. The 300 stays, and the derivative of 2t is, again, won't need you to memorize what the derivative of 2t is, but in the case of homeworks, I might ask you what that is. But anyways, the derivative of 2t is the natural log of 2 times 2 to the t. So the population is growing at a rate of 300 times log of 2 times 2 to the t each hour. Okay, so that's absolute growth rate. How much is this growing percentage-wise? Well, that's when I take p prime and divide it by p. So that's 300 log 2 times 2 to the t divided by 300 2 to the t. Well, 300s cancel, 2 to the t cancel, and I'm left with the natural log of 2, which corresponds to about 69%. So the growth rate, the percentage growth rate of this population is about 69% per hour. That's about the rate at which it's growing. But notice that even though, yes, the population doubles each hour, that's 100% growth rate, this is talking about an instantaneous rate of change. So we're actually going to get a smaller percentage rate when we look at instantaneously. On average, the growth rate is going to be higher than this instantaneous rate of change. Okay, here's question 1. A population of 20 deer released in a nature preserve as modeled by the equation p of t is 40 divided by 1 plus e to the minus 2t. T is the number of years after the population is released, and this is the number of organisms. So A, let's find p prime of t, and then B, let's graph and interpret both p of t and p prime of t. Finally, let's do a social sciences type of example, and we're going to do some economics. This is marginal cost. Economics, a lot of the models in economics were actually developed in analogy to a lot of models that get used in physics. So since physics uses a lot of calculus, it's not a surprise that calculus then is used in a lot of economics models. So marginal cost. If C of x is the cost of producing x goods, then C prime of x is called the marginal cost. And what this is, it's the cost of producing one more good. If I'm making x goods, how much is it going to cost me to produce one more? Generally, we expect diminishing returns, which is at some point making more and more of an object is going to be more and more costly to make an object, because as our operation scales bigger and bigger, maybe the cost of maintaining all of the labor gets harder, and the cost of centralizing a really big operation is a lot bigger than controlling some sort of small company. Anyways, microeconomics says that in perfect competition, a firm will maximize its, I should have said profit here, when its marginal cost is equal to the price of whatever the object is, the price that a consumer will pay when it buys it. This is because If it costs more to make one extra object than you're going to be getting back in terms of the price of the object, then it doesn't make sense to make it. So, the price of producing X items in dollars is given by the function c of x is 1,000 plus 5x plus 0.01x squared. If the items can be sold for $15, how many items should be produced by a profit-maximizing company? Well, the marginal cost is, according to the derivative of 1,000 is 0, the derivative of 5x is 5, and the derivative of 0.01x squared is 0.02x. So we solve for x, subtract 5 from both sides, divide both sides by 0.02, and we get x equal to 500. So this company should produce 500 goods if it wants to maximize the profit that it gets by producing these goods.